We can get started. So today I want to be talking about GPT-3. Specifically, what I want to be doing is going over the paper. So we're gonna be, I'm gonna try to see like how much we can get done in an hour, but just go through the whole thing. And what's interesting about this paper is that, so first off, it was a request from a friend. Like Lucien asked me to do this episode. But also, like, I thought it was funny that a lot of people tried to predict my position on this paper, thinking I would say, like, oh, I don't think this is interesting or novel because it's just a paper about scaling. That's not what I think at all, actually. I actually think it's an amazing paper. I think it's extremely promising, and I think, obviously, like, people are going to do a lot more work to improve this. That said, I often feel like if you want to criticize a paper that's like 10 times better than yours at predicting some language model task, well, if you think it's dumb and you can't beat it, well, what does that say about your own work? So I think it's more helpful here to be humble and actually go through this thing and actually understand how it works. So that said, like, one of the interesting things about this paper is that it barely covers the actual algorithm. Like, most of this paper is actually about going, like, evaluating different data sets and tasks. Like, that's what the 75 pages are about. And there's maybe about like 2 pages like devoted to the actual like model. And so just like as I thought it would be helpful background, like, let's just kind of go over like sort of the basic knowledge you need to figure out how these models work. So the simple use case we're going to be looking at is assume that we have some sort of language model. And so our goal here is, like, let's say we have some sort of sequence. Let me just do this. And then, we're doing some sort of translation, right? So then the task could be like, I, and then coming here, like, I am Mark, for example, right? So why is this doing this? So I will also say, like, feel free to ask me questions. Like, I don't feel like particularly compelled to actually finish this. I could always just do another talk to finish it. Yeah. So this is sort of like, let's say we have this sentence, right? And then we wanna translate it. So each of these is a token. So like each one of these is a word. And typically, like I said, we want to translate this. So basically, you want to feed this to some sort of black box here, and then some like deep neural network. And what you want to get out, ideally, is a translation. So what you want to get out is here. Like, it'll be something like je suis Marc. Like, let's say we're translating to French. So how does this work, right? Like, so historically, whenever we're doing any of these like sequence tasks in machine learning, we typically use like something like a recurrent neural network. So just like a sort of background, like, let me just show you how this all works. Yeah, there we are. So typically, so each of these x's is the tokens, and then your O is, like, let's say, so this would be I, and then this would be je, right? And then this would be, like, let's say Mark, and then go to Mark. And so at every step, you have a hidden layer, and this hidden layer basically takes in all of all of your past inputs as a sort of single like giga represent. Maybe I'll just draw it; it'll be simpler. So basically here, like Sui, for example, will take in the output from what the network says about je. And so it basically takes in everything like as a single line. So it looks something like this. However, like, one of the innovations with transformers, which is the sort of main architectural innovation that GPT is inspired by, and And like I said, like if you want to learn more about how to implement transformers, I actually have a whole other separate 2-hour video about this on YouTube. It's probably, we'll go into more detail. But here's the idea. So like, let's say you want to translate suis. And so ideally, instead of just knowing what je is, you could also like add these connections from all of the past words. So it would look something like this. And then similarly, like Mark here would take in like this, it would take in this, and it would take in this, and it would take in this. Like it would take in everything. And so the idea here is that as opposed to just telling the network, like just pay attention to the past encoder input, you tell it to pay attention, you give it the option to pay attention to all other input tokens. And so the idea is then that this helps you build like much more robust translations. So specifically in GPT-2, so like the precursor to GPT, this works in a sort of left to right fashion where at every token basically, I'm just going to do some scribbles. It's an arrow like here. So let's say we have a certain word here. Then we want this word to pay attention. So let's say this is a word at the output. We want it to pay attention to all of the inputs before it. Such that, like, let's say this is your output t. Then this would be all of your inputs from I0 to t minus 1. Right? And so the idea here is that, like, so these will be like each their own token. And again, like I said, if you want to actually see the code for this, like just go to my other tutorial. I kind of covered this like in a lot more detail with the mechanics of how to actually turn this into PyTorch code. But the idea is this, like basically like here, you're saying, okay, well, like to figure out how to translate this word, I want to be able to pay attention to all of the other previous inputs and all of the other previous and the previous output. So like it'll also be O of 0 to O of t minus 1. So different transformer architectures change in this sort of decision. So for example, other transformer architectures will allow you to, for example, have a dependency from O of 0 till O of big T, which is basically the end token. Or you could say, oh, like, well, instead of paying attention to all of I of 0 to t minus 1, like maybe you just want to keep track of one small range. So like, let's say I of 0 to I of k, where k is a lot smaller than t. So this would be like so this is like the people would give it a name like localized attention. Or you could like hard code these, like let's say you can make them skip a connection, you can make like the connections random. So there's like a billion different ways you can actually do this. Like there is definitely not just like a single proposal. But the main thing like I want you to keep in mind, like for this talk at least, is that when it comes to GPT-2 and GPT-3, which is like very much like a direct sequel, is that the attention mechanism is like left to right. So you're only dependent on words that you've already seen before. So like what's interesting about the title of this paper is that the title of this paper is Language Models Are Few-Shot Learners. It doesn't say GPT-3 is great. It doesn't say we beat state of the art. You know, it's saying few-shot learners. So what does that mean? What's a few-shot learner and what's a language model? So at a very high level, a language model is this. So a language model is basically a model. So let's just call it like P, right? That takes in that tries to predict the current word given all past words. So this is what a language model is. And so you can see like this why this works well for generative tasks, because like for each point you ask the model, okay, well, what's the next word you can provide me? And this is why this is why this works this works fine for generative stuff. But so what's a few-shot learner then? So a few-shot learner is like when you think of historically like what we've done with natural language processing, is that when you come in, you pretty much like come in and you build like let's say an embedding model. So you train an embedding. So or sometimes people call this like pre-train an embedding. Sorry, I think I'm getting a network issue. Let me just make sure this works fine. Okay, yeah, it does. Sorry, it's just an issue from like the laptop that I use for chat. Anyway, yeah. So typically you pre-train an embedding, and basically here like you're trying to learn some sort of like by where your objective function is this. Like basically this is your loss, is trying to predict like the next word. But then you actually train on a variety of different tasks. Like for example, like you would then take, so this gives you basically, you know, a model. So here you end up with a model. And then you take this model and you train it on a whole bunch of other tasks. So like, let's say, let's do an example. So you could, for example, say, okay, well, I want to train this on translation. Or you could say, I want to train this on like generation. Or you could say, well, I want to turn this into get me a React, like English to React app, etc. And you could think of like a whole bunch of tasks that you could fit like this. But typically, like none of this is magic. Like in any sort of supervised learning task, like the way this would work is that you would still need to have examples. Like you would need to have input data and output data that maps to it, and then you know you can then come in and actually train something that works here. So basically, that means that you have to train k different models for k different tasks. And this feels kind of weird, right? Because on one hand, you would expect, well, if someone knows how to translate text really well, then, you know, you could reasonably expect them to generate text really well. So the main thing I love about this paper is that this is the problem it solves. Like, as opposed to having to train k different models for k different tasks, what you do is you train one model for k different tasks. So this is basically GPT-3. And the idea is you can do this very easily with a large language model. So this is sort of like, you know, if you if you want sort of like a high level summary of all, like of everything that I'm going to be talking about today, like this is going to be the overall theme. So yeah, let's just keep going. So if you go through the paper, like they say like that they've been able to get state-of-the-art performance. So GPT-3 is autoregressive. So autoregressive is what I talked about earlier, as in it's only dependent on the tokens that are to its left, with 175 billion parameters, and this is 10 times more than any sparse than any previous work. And so they tested out on all sorts of stuff, like unscrambling words, finding novel words, doing 3-digit arithmetic. And so let's just go over all of these use cases right now. So, like I said, so typically here, you will have, depending on the sequence that you, like depending on the specific task that you have, so this is what each of these sequences mean here, you're going to be training like your own model from scratch. And there's no like basically cross-learning among these models. However, the idea is then instead of feeding a model like the task as a data set, so for example, like instead of saying like, okay, well, yeah, this is my input and then this is my input data, this is my output data or labels, and feeding this and training via SGD. So this is what it would be typically here. So instead of doing this, what if you could instead just basically give the language model a prompt? So for example, you tell the model, can you talk in the style of Elvis Presley? And then you give it a few examples. Like for example, you would say, hey, how's it going? And then this would, I don't know, maybe you'd say translation here is like, how you going, baby? I don't know if this is how Elvis talks, but let's say if it is, you give it a few examples like this, and then you give it a novel example. So this is a key point. Like, well, you're not actually retraining the model via SGD. You're actually just giving the network a few examples of what you want it to look like. So there's no new training happening, but you're just giving it examples. And whereas like with SGD, you would need to run this expensive training loop each time for each new kind of model that you're doing. One of the reasons why people are losing their minds on Twitter like about GPT-3 is that this just kind of works. And of course, it's not ideal. Like you could, let's say, feed it better prompts. Like some tasks like may not be sensible. But I still think it was a sort of ridiculous achievement if you just look at this in the sort of the base case. So basically here, like you'll see here, first off, that when it comes to here, like let's say you look at the number of parameters, like first off, like it's just an order of magnitude increase from anything that we've seen before. So like let's say in the past, like the largest one was 13 billion. And if I'm not mistaken, this was just GPT-2. Whereas now we're talking like, okay, well, 175 billion parameters, you know, just absurd numbers. And also, like you see here that the accuracy typically for 0 shot versus 1 shot versus few shot doesn't change a lot. Whereas for these really large models, it seems to do. And so I'll describe what's the difference between all these. So 0 shot would be you come in and you tell a model, I want you to translate in the style of Elvis Presley without showing it any sentences. 1 shot would mean you would give it a single example. You'd just be like, here's one example of Elvis Presley talking on 1 sentence. And few shot means you give it a couple. So it's sort of a small data set. But again, even though it's a small data set, you're not actually doing any sort of retraining with something like stochastic gradient descent. So here. Yeah. So this is like this is a sort of an example of what I was talking about earlier. So let's say 0 shot would be, you know, translate English to French, and here's the word cheese. 1 shot would be, here's one example of a translation, and few shot is a couple. So obviously you would expect performance on few shot to be better, but the fact that it is even possible without doing this model, which is like sort of the traditional SGD model, to me at least is mind-boggling, and for me is like the most impressive thing about this paper, a lot more so than the memes going like, well, this is a big model. Like I think people saying these things are just like sort of like missing the point of why this work is interesting. So sort of benchmarking here. So one of the things you'll notice in this table, so this is a table comparing the model parameters, the number of layers, the dimensionality of the model, like the number of attention heads. So just everything is bigger in GPT-3. So first off, you'll see here, so GPT-3, the 13 billion, like this is actually roughly equivalent to GPT-2. You'll see here that the number of layers is 96. And, you know, you could expect with GPT-5 and 6 and further iterations of language models, this to keep increasing exponentially. The number of layers is going to increase. The interesting thing here is you'll notice the learning rate is very small. And the idea is because like these networks are so large is that their training is relatively unstable. And so having a really small learning rate is great. Another thing you'll find interesting is the batch size is 3.2 million. So this is not data set size, it's batch size. Which basically means that, like, you know, there's no way you're actually going to get this to run on a single GPU. Like a batch is distributed over multiple GPUs. And it just goes to show you that part of what's really impressive about this work is, again, if you want to just view it from a purely scientific standpoint, I think you're missing the point. Like this is definitely more of an engineering accomplishment that has unlocked new capabilities in science. And if you view it from that lens, this work is extremely interesting. So the model architecture, they also say, like, hasn't changed from GPT-2, which is actually really interesting. Like they didn't even bother. They're just like, okay, well, what would happen if we scaled it up? And the data set they use is this. So they use a data set called the Common Crawl. They use the web text, they use books and Wikipedia. So basically you're feeding it unstructured text from the internet. You're basically just feeding this whole thing the internet. And so it's going to learn everything from the internet, good and bad, because there's all sorts of dumb stuff being said on the internet. But that said, it's sort of remarkable that this works in this fashion, because typically people are used to having to feed data sets like these, like labeled data. Labeled data is generally an issue because either it means that you're breaching people's privacy by reading them. Like, this is not the case for publicly available internet. But more importantly, like, it's just expensive to label data. Like, you need to come in and pay someone to actually look at the example and label it. You can't just get super cheap labor for it either, because, like, let's say people don't have the domain expertise to label something correctly. Then garbage labels are actually worse than having no labels at all. So going here, like, you'll see that there's sort of this, you know, like they measure total compute in petaflops per day. You could use all sorts of metrics like number of GPUs, but flops is like a good one because it normalizes things across qualities of GPUs. And then the way they train it, so here you'll see is like they trained it on the V100 GPUs. So this is sort of like the standard GPUs used in most NVIDIA benchmarks. Like, I would expect these to change to the A100s very soon. But the interesting thing about this is that, like, here, like, let's just start looking at this. So this is sort of I would say, like, a trend that definitely upsets people that are very theory-minded. But basically what this is saying is, like, look, if you increase the number of flops, you're gonna decrease the validation loss. And so this is sort of part of this trend of, like, Richard Sudan's article, like, The Bitter Truth, is that you could sort of come up with all sorts of complex mechanisms to do language or machine learning in general, but turns out a lot of these mechanisms are just beaten out by scale. And so, and if you can't, like, you know, beat something that you consider dumb, like, maybe, you know, you should evaluate whether your work is actually all that intelligent in the first place. So let's, like, look at some of these data sets. So let's see here. So for example, like, here's one, like, so this is Lambada. So this is like basically word completion. So Alice was a friend of Bob, and Alice went to visit her friends, Bob. What's interesting about this task is that you don't need labels for it. So what you could do is you just come in and randomly zero out, like, mask some of these words. And so you basically get free training data. And whenever you can do this, like, that's great in ML. Like, people call these techniques in general self-supervised learning. But anytime you can turn your problem into a self-supervised learning problem, on one hand, you're going to need a lot more compute. But on the other, you don't need labels. And that's always great. So you could always get, you know, it's cheaper to get more like more data that and with more compute, as opposed to spending money on labeling data, because, like, your time is more valuable than a computer's time. That's how you should think about that. So let's see here. So and this, there's a couple of data sets that fall into this trend, like, let's say the story close, which is like finish off the last sentence of a word. Others are like trivia. So trivia is like another example of this idea where, you know, you could imagine that, like, if you have the question and answer as part of one sentence, then trivia basically becomes predict the next token. And you'll see here, essentially, like, they have here the fine-tuned state of the art. So this is, you know, like, let's say here, this line would have been, like, I wish they actually also added the number of parameters this took, but you'll see here, like, this is not actually beaten by the 13 billion approach, but it is beaten by the, so it is beaten with, like, the larger models, but only for few shot. And so, but the fact that one shot and zero shot even come close to state of the art is incredible. Like that to me is still, like, actually very impressive. But the fact that it beats it is also even better. Like, it just tells you, like, yeah, like, maybe, you know, I don't know, we're not as smart as we think we are. So translation, for example, you'll see here, for example, they show you, like, the state of the art from, let's say, English to French and English to German. But then when you actually look at the performance of GPT on zero shot on translation, it's actually not very good. It's actually very far away from state of the art. And that just goes to show you, like, it's like, I mean, it's just a harder problem. Like, let's say if you asked me to translate from a language that I've never seen before, like, why would you expect me to do any good on it? And even though, like, if you look at the few shot, or the, like, let's say you give it a bunch of examples, it still doesn't beat state of the art, which is very telling. It tells you that, it tells you that these sort of, like, custom models will still probably be better for now. But the idea necessarily, like, I don't want you to read this as to say, like, okay, well, because this was 10% lower on average than state of the art on the translation, therefore GPT sucks. I think the more honest intellectual approach would be to say, well, what if I scaled this, like what if I added another zero here? Like, what if this became like a trillion or a petabillion or whatever? Just, make it bigger. Would this reduce this gap? And I would venture to say yes. But obviously, it's a very expensive experiment to produce. So I'm not going to be the one to answer that question. It's probably going to be researchers, a couple of labs that can answer this, like OpenAI, Google, Facebook, Amazon, Microsoft. Like the only researchers there that have the budget to spend these kinds of compute budgets will be able to definitively answer this question. So typically, translation tasks are also rated on their distance from a good translation a human made, and so this is the blue metric. So you can sort of think of it like a distribution metric, where you look at the distribution of your words versus the distribution of the actual translation, and just measuring this difference will give you an idea of how good your translation is. So what's Winograd? So is a classical NLP task that determines involving which word a pronoun refers to. Oh, okay. So let's say like I have in a sentence like Mark's a great guy. You should talk to him. So referring to him, like being able to associate him with Mark here is sort of like an important task for, like, let's say task completion, or let's say we're emailing each other and I want to build some sort of ML system that figures out like who has the task, who has the action item, so that I can automatically populate it in Jira, for example. Like this is where this is really relevant. So let's see here. So turns out, like here, if you look at GPT-3, it looks like it gets state of the art. It just crushes it. Even crushes it at the fairly lower end of data volume. So I would expect like maybe this task was already beaten in GPT-2. But I'm not going to go ahead and read that paper right now. Yeah, so let's say here, like another one is comments like reading comprehension tasks. So reading comprehension tasks like are typically like you have some sort of text, like let's say this is very SAT style. Like, like here is a story of Mark and Joe talking about something. And then like, the question could be, well, what was the most important thing to Joe, right? And so this is again like a hard problem for humans, even because like I remember doing SAT tasks, like I didn't find these kinds of questions particularly interesting or engaging. And so the fact that, again, you can, like, if you look at the fine-tuned state of the art, so these are a bunch of different data sets. Like I don't know what most of these are, but I've worked with Squad, which is a question answering data set. That's what that stands for. But you'll see here that like with zero shot, it's not very close, except on Coca, which leads me to believe that maybe Coca is just a much smaller data set, or that this data set occurred in the internet. So a common trend in this paper is that, well, in machine learning, we have this idea that overfitting is bad. And overfitting is bad because it ultimately reduces your test performance. But what if the entire internet was your data set? Then you would expect that because it's such a massive data set, maybe overfitting isn't that big a deal anymore. Like, I know this will be a very controversial claim to the more theory-minded people. Because, of course, new content to the internet may not fit the same distribution of the existing internet, but maybe it gets pretty close. And so this is kind of like, and as a sort of way to support this, like I would claim that, sort of the, so, I mean, it's not that compelling, honestly, like 23 per 23 here. But, if you look at zero shot, like few shot, like, again, you're not retraining an SGD loop, but the perf actually still gets pretty good. So again, like a lot of here, like by few shot, by the way, they also mean 5. This is very small. Like, I mean, ideally, if you wanted to actually be very, I think here OpenAI is sort of underestimating things, but let's say their few shot was instead the entire data set, the entire training data set, where the entire training data set is maybe like 1 million examples, then I would expect this curve to go up even further. So let's see here. So this is an interesting one. So so let's say you come in and you want to test out arithmetic. What's interesting about arithmetic tasks is it's one of those tasks where you don't need to generate new training data. Why? Because you could just like, let's say, create a textual data set where you go like, okay, well, you pick two random numbers and then you sum them up and then you turn that set of those sets of integers into a string. And this lets you get like an infinitely large data set on which you can test out your models on. So again, it's very amenable to this sort of self-supervised training regime. And so, like, again, you could do this for subtraction, you could do this for two-digit addition. And if we look at the performance here, like on the accuracy, like it does really well on two-digit addition, it does really well on two-digit subtraction, but then it sort of tanks here. So what's this? Purple is four-digit addition, and then what's gray? Gray is five-digit subtraction. So the more digits that you add, the worse this gets, and the accuracy gets really bad. Okay, so here, for example, I'm not particularly compelled that this is a good result, just because you could argue that, let's say it's parsed some sort of, you know, like math homework website, homework for kids, for example. Like, let's say it parsed a website that looks like this. You know, let's see. So I know this is text, but let's say it parsed something that looks like this. Then you would expect it to maybe just like memorize these results, like, because like there's not that many of them. There's, you know, you could have 99 possible two-digit numbers, like 90, and then, you know, the subtraction of two of them, so it's 99 times 99 choices, which is 99 times 99. Which is, you know, it's a big number. It's like 9,800, but it's nothing in comparison to the 175 billion parameters. So you could reasonably expect the model to have just memorized everything here. So actually, this is not something I'm very optimistic about, like this sort of symbolic reasoning. And so, and if you look at tasks that talk about like these sort of like, oh, like GPT is going to help us automate code, I don't think that's going to be the case. I think it'll help you automate simple code. And so it'll help you, let's say, it sort of replaces Stack Overflow in a lot of settings, but it doesn't replace programmers. I think people that talk about programming being replaced as a discipline is extremely sensational. I think programming is probably going to be the last job that gets automated out of all jobs. I mean, that and very physical, like, you know, physical jobs like that involve like robots with some very fine, you know, fine tuning, like some craftsmanship and stuff like that. But I don't know. But then again, like, you know, I want to show you this. Like, this is a skull that I have printed with a 3D printer. You know, I don't know of any human that could necessarily design this. Like, I'm sure some of them exist. You can see some of the fine details in the mesh here. But yeah, like, I mean, all 3D printers can solve this. Most humans probably couldn't do this, and that's very telling. So again, and this is a common trend here where you'll see that the performance tanks for multiplication. Well, because multiplication is inherently a more difficult task than addition. But yeah, so, and then if you look at the end level performance, here, like, what's interesting is you don't actually need to measure the accuracy relative to another model, because you know what the best accuracy is. It's just, you just give the numbers to your computer and it'll figure out. It's actually how you generate the data in the first place. So let's see here. So word scramble. So to test GPT's ability to learn novel symbolic manipulations, we designed a small battery of 5-character manipulation tasks. So the model is given a word with its letter cycle and is expected to generate the original word. Okay, so you reverse the word, you flip the characters around. Okay, how does GPT do here? So for random insertions, it's best at figuring them out. For reversed words, oh wow, it completely tanks. I wonder why that's the case, like, because I would have expect random flippings to be harder. Do they talk about this? Let me see. In context words, reversed words. Okay, so they don't actually talk about why this is harder for reversed words, but I'm kind of interested in this. But it sort of reminds me, like, let's say if you're doing an algorithm like quicksort, it runs the slowest on reversed lists. Even though, like, if as a human you looked at a reversed list, it's actually very easy for you to figure out how to reflip the list. Like, just, you know, I don't know, flip the page, and then all of a sudden you have the sort of list in big O of 1. Whereas, like, quicksort will take, like, a squared time. So another task they talk about is SAT analogies. So for example, I actually find these really hard. Like, thank God, like this wasn't in the SAT when I was doing it. Like I think they had removed it the year before because they thought it was too hard. So audacious is to boldness, as sanctimonious is to hypocrisy. Okay, sure. So I don't even know what this means. Anonymous is to identity, as remorseful is to mislead. So how does GPT do here? So again, you see the performance increases a lot better with a few shot. Yeah, so here they're trying to explain one thing. Like often when you think of random guessing, like you think it's a coin flip. But coin flips are only somewhat good on a binary classification where you're trying to say yes or no. But for generating a word, it sucks, because especially let's say you have 5 choices, then it's 1 over 5. It's a 5-sided coin. If it's generating a word from a dictionary, then it could potentially be 1 over the number of words in the dictionary. So the fact that it gets any performance at all is pretty good. And in fact, one of the things I'd be curious about is like, how well do humans do? And as a sort of proxy for that, you could actually just go ask the SAT committee how well humans on this. Like, we do have labeled data here. So another one here is like news article generation. So this one is interesting. Like actually, I had this conversation with someone like fairly recently where a lot of training data sets, actually with Rave, like with his D&D data sets, a lot of data sets for summarization are for news. And so if you then try to apply them to other domains, like let's say poetry or Dungeons and Dragons or anything else, like they end up being really, really bad. And so this is not a coincidence. It's probably like, reasonably just memorizing your existing data. So let's keep going. So let's say, so this is a GP, and then like, there's sort of a lot of generative tasks you could turn into classification where you give it an example and then you ask it, like try to distinguish it whether is this a human or is this a robot. You could also do the same thing with a human, like give a human an article and ask them to wonder, is this a human or a robot? So here, for example, like this was an article that humans found really easy to distinguish. I think it's because they use trivia knowledge, like stuff like with Megyn Kelly and Joaquin Phoenix. And so this seems like somewhat of an unreasonable discussion, which is why humans would find it really hard. Whereas here, like let's say the United Methodist Church, something about, okay, 10% left to, yeah, so this does look like a somewhat reasonable news article. So I can understand why, but again, like this is sort of cherry picking here, and ideally, let's see, so, oh, okay, so so mean accuracy versus control, okay, yeah, it's a lot lower. So, so they sort of talk about this now. So how can we make sure that we have it like memorized our data set? So for example, like one example I'll give you here is like, let's say, you come in and you try to feed the model like a few shot examples of translating from Elvis Presley. Well, it turns out, like unknowingly to you, there were like a couple of people. So how can NLP cover those? Vitalik mentioned the model makes human-like errors. Okay, so I have a question from Lucien. So question on arithmetic tasks. How can NLP cover those? So Vitalik mentioned the model makes human-like errors. For instance, 243 plus 176 equal to 400 as opposed to 410. Is this noteworthy? Yeah, so let's just go over the NLP, the task here. So if you look at the performance here, so first off, as a brief point here, generating data for arithmetic is very easy because you can just like tell your computer to generate 2 random numbers and then add them and get the correct result, and then tell it to just append all of this to a string. So now you can just have this infinitely large training data set that you can use. However, the sort of human-like error here is very easily explained in the sense that you're saying here like 234 plus 176 is equal to 400. I believe the reason why it would make this kind of mistake is because you're crawling the entire internet. You're going to end up crawling data sets that look somewhat like this, and some of them are going to be filled out with those actual mistakes, and then the model is going to come and learn those mistakes. So it's not that the model is learning to be more human, it's just that the data that's being fed to the model is bad, therefore the model's results is bad. One way to potentially amend this mistake is to you yourself generate a bunch of digits that you can add up create a whole bunch of websites where those results exist. GPT then comes in and memorizes them, and then it won't make these same mistakes on 3-digit numbers. That said, I still think even if you do this, you would still probably find those mistakes in 4-digit or 5-digit, because you can see here that the performance absolutely tanks here. Like, is just awful. Whereas, like, you know, any computer, like, even though this is a supercomputer with thousands of GPUs or whatever, it doesn't do well, even though, like, your laptop can run these results and, you know, not make these mistakes. That said, your computer isn't getting an ambiguous representation, but it just goes to show you, like, how far off computers have to go. And, you know, any sort of reasonable person that has, like, a 6th grade education would probably be able to add 5-digit numbers without, like, much compute. So it's not like we're comparing, like, the best humans with the best computers. Like, we're just comparing very average humans, very average computers, and they beat the supercomputer on this task. Yes, it's text, not an integer, but still. So here, for example, yeah, they show this here, like, okay, what do these lines mean? So we measure model performance during training on a deduplicated validation split of our training distribution. Though there is some gap between training and validation performance, the gap grows only minimally with model size and training time, suggesting most of the gap comes from a difference in difficulty rather than overfitting. Okay, so here it's just the number of model parameters. So the thick ones are the highest model parameters. Okay, oh no, it's the opposite. The yellow ones are the highest model parameters. And so the more you increase the model parameters, the more the validation loss decreases. Yeah, so this is an interesting point, because on one hand, you could reasonably do these validation splits, and then you could always say, well, I'm going to train on a subset of this thing and then figure it out. Although, like, I wonder here, like, when it comes to their training data set, are they still comparing the training data set on an entire internet, in which case there is going to be invariably a leakage. So let's see here. I think they addressed this here. So on one hand, the data set and model size are about 2 orders of magnitude larger than the dues for GPT-2. On the other hand, precisely due to the large amount of data, even GPT-3 does not overfit by a significant amount measured relative to the held-at validation set, which has been deduplicated. Thus, we expect the contamination is likely to be frequent, but that its effects may not be as large as feared. I don't know about this. Like, I mean, I understand. Like, in fact, I would just maybe, I wouldn't necessarily go as far to say as to, like, there is no overfitting here, that there is no contamination. But I guess my uber level point is that for most tasks, like, let's say arithmetic is an exception to this, but for most summarization tasks, is overfitting actually a big deal if you feed it the entire internet? So moving on here, like, let's see what they talk about the limitations. So has several algorithmic limitations, which, okay, include bidirectional architectures. Okay, yeah, so I mean, they could have reasonably fed it a bidirectional architecture here. It would probably be better. They didn't. You know, they could also work with sparser models. I think here they use denser models. But again, the fact that they were still able to get good perf without any of these additions is still a great thing. Yeah, and obviously, like, the fact that these are expensive models, like, I mean, like, we're sort of getting in this regime in language where it's become sort of like particle physics, where you need, like, your Large Hadron Collider to be able to run any sort of reasonable experiments. And so, and it's not entirely obvious to me that this trend will actually be reversed. Like, it does seem likely that smart small models will be beaten by dumb large models. And it could just be a bit of truth that we need to accept here, even though it, like, opposes sort of these nice ideas that we have around, like, how our brains work and how around compression works, around how the brain is power efficient. Like, yeah, maybe, but or maybe not, and maybe, you know, we're going to continue being beaten by these techniques. So they also briefly, like, let's see here, like, what other limitations do they talk about? So they say it's pretty weak in text synthesis, but the overall quality is still pretty good. It has some algorithmic limitations around, like, the bidirectionality and sparsity. It has poor sample efficiency during pre-training. Yeah, so basically, like a human doesn't need to be fed the entire internet before they can do interesting tasks. Like they're fed a lot less data. And so how come? But at the same time, like, I mean, this is sort of a hard open-ended problem. And even then, like, it's not entirely like, I mean, yeah, it is actually. Like, let's say if you looked at the total number of word utterances that a human is being fed from their childhood to their adulthood, it's going to be many orders of magnitude less than the training data set that GPT was fed. So they also say there's some potential harms. Like I think some stuff like they talk about was like impersonation, like disinformation, bias, like where like the model is just going to reflect biases that are internet. So if the internet is racist and sexist, then it's a lot easier for these models to be racist and sexist. And they sort of talk about this here. Let's see, sentiment across models. So for example, interesting, this varies across data size. So let's see, we're Middle Eastern. So the more data you feed it, the less it ends up liking Middle Easterners. Black people are liked more with more data. Who's like Latinx are liked a lot. It's like I don't know about this visualization, guys. Like it doesn't seem to make the most sense to me. Like why should the sentiment vary across the data size? It just seems to me like maybe there's at some points there is just like a peak of data that's positive about certain races. Otherwise, I wouldn't pay too much attention to this. Yeah, so the energy usage point I think is a funny one. It's sort of like, well, you know, cars use too much energy, so let's not use cars. Like, I don't think this is a real concern. I think that if anything, you know, we should figure out how to use more energy efficient ways to train these models. So maybe if we go to nuclear energy or stuff like that, like all of these concerns become invalid. It's not like, you know, we're dumping coal inside of a big furnace to be able to train these models. And yeah, it looks like that's pretty much it. That was shorter than I expected. They have some details around the data set, some details around the model training. But yeah, like a lot of this paper is like very extensive benchmarking. That's why it's such a big paper. That's why it's a team as well that generated this, because like odds are like a lot of these people spent a lot of time doing all of these benchmarks, getting wrong results, fixing them, making improvements to the model along the way. And so that's pretty much it.